Hello, everyone. Welcome to our UHN AI Hub rounds. And today I'm extremely happy to introduce our speaker, Dr. Jun Ma. Jun is a machine learning lead at our AI Hub, and his research mostly focusing on developing cutting-edge algorithms for accurate, efficient biomedical imaging parsing with the goal of enable precise cancer quantification and personalized patient care. Jun has published numerous papers in top-tier journals such as Nature Methods, Lancet Digital Health, Nature Communication, and although he's still considered very young scholar, his citation already exceeded 10,000 citations, which is extremely impressive. And he's considered the world leader in particularly in the areas of biomedical image analysis. And today he will talk about some of the research he's been doing at AI Hub, mostly focusing on foundation models for biomedical image analysis. With that, Jane, please take away.
Okay, thank you, Dr. Wang, for the warm introduction. I also want to thank Dr. Xavji, Dr. Wang again, Kelly, and Gata for organizing this event and for the opportunity for me to share our biomedical image research at AI Hub. Yeah, it's a really great pleasure to be here today, and I'm grateful to all of you in the audience for taking time to join us. Today, I'd like to talk about advanced foundation models for biomedical image analysis. Oops. Okay, before we dive into the details, I want to highlight 4 key messages that will anchor today's presentation. Those reflect both the current status and the future potential of AI in biomedical image analysis. Number 1, foundation models are unlocking new possibilities for generable and scalable biomedical image segmentation. Instead of training specialist models, foundation models enable us to develop universal solutions that can segment a wide range of medical images and cancer types in a zero-thought manner. Number 2, multimodal generative models offer tremendous potential to reduce experimental cost and clinical burden. For example, we could use AI models to simulate the effect of perturbation in microscopic images instead of doing lots of manual wet lab experiments. We could also use AI to draft radiology reports rather than writing from scratch. Number 3, agentic systems provide a powerful framework to unify diverse AI models. These systems act as intelligent coordinators that can plan, reason, and interact with environments, making it possible to combine multiple AI tools into end-to-end workflows. And finally, now this progress is possible via deep collaboration between AI researchers and clinicians. In addition to showing our AI capabilities, I also hope this presentation can motivate more collaborations. I strongly believe that AI Hub is uniquely placed and resourced to facilitate more collaborations to co-develop clinically meaningful and safe AI solutions. I will use the AI models we developed at AI Hub and some collaborative projects to demonstrate those 4 points in the next 15 minutes. This is today's outline. I will be starting with introducing our medical image segmentation foundation models, followed by presenting the multimodal models for perturbation prediction and report generation, together with the agentic system for X-ray image analysis. Finally, I will share some available resources, including models and datasets that can be used to prompt further research. Okay, let's move on to the first topic, biomedical image segmentation foundation models. So first, what is segmentation and why it is important? So basically, segmentation aims to delineate the boundaries of various organs, tissues, and lesions in a fully automatic or semi-automatic way. Those algorithms have a wide range of applications. For example, by segmenting the organs, lesions, and surrounding vessels in CT scans, we can use the 3D reconstruction results for cancer early diagnosis and surgery planning. Similarly, by segmenting various cells and organelles in microscopic images, we can use them for cancer microenvironment analysis. In a word, segmentation is a core technology towards precise biomedical image analysis. Actually, segmentation is not a new task. It has a long history with half a century. Here is a brief timeline. At the very beginning, people usually use a heuristic method such as thresholding, region going. Those simple methods can only rely on naive image intensity information, which cannot handle complex biomedical images because of the effect of noise and inhomogeneity. From 1980s, with the development of variational models, segmentation is usually formulated as an optimization or mathematical model-based task. We first define this energy functional with regard to the segmentation counter. Then an optimization algorithm is designed to solve it, and the corresponding minimizer is a final segmentation counter. Those models are transparent, but they cannot directly learn from large-scale dataset. Starting from 2015, deep learning-based methods such as convolutional neural networks dominated this field. Typical models include UNet, FCN, DeepLab, and so on. The key feature is that deep learning neural network can learn representations from data in an end-to-end manner. However, those models are usually tailored for specific tasks or image types which have limited generation ability. With more data and more powerful computing available, in 2023, segmentation enters foundation model era. The milestone study is segment anything model, termed as SAM, that was trained on 11 million images with 256 GPUs. What are foundation models? This term was conceptualized by an expert consensus from Stanford University. Essentially, foundation models are still deep learning models. Those models are usually trained on broad data that can be adapted to a wide range of downstream tasks. There are key features of foundation model. First is its strong generation ability. The pre-trained foundation model can be directly applied to a wide range of tasks in a zero-sort manner. A second feature is its flexible adaptability. We can quickly adapt a foundation model to a new domain or new data type with limited labeled data. In the field of medical image segmentation, the first foundation model is the segment anything model developed by Meta AI Research. This is a promptable segmentation model, allowing users to use various prompts to specify the segmentation targets, such as points, bounding box, mask, and even text. The model is trained with 1 billion image mask pairs from 11 million images. Here are several examples to show its capability to segment diverse image types. Let me use a figure to show SAM's impact. SAM was released in 2023. Since in just this figure shows the number of citations of this work. So in just 7 to 8 months, SAM has obtained over 1,000 citations. So you can feel how crazy this field is. Here are two common types of studies built on SAM at that time. One is to benchmark SAM on different datasets or different tasks. Typical title includes can SAM segment ABC, SAM struggles in ABC, or SAM meets ABC. The other is to combine SAM with other models. For example, one can combine SAM with detection or semantic segmentation models to get the category information. One can also combine SAM with tracking model for video segmentation. Furthermore, one can also combine SAM with generation model for image impacting. In medical domain, we care about that where SAM can segment medical images. So the answer is no. So here is one of the most comprehensive study that benchmarks SAM on various medical image datasets. And the left column corresponds to ground truth, and those right columns correspond to segmentation results based on different prompts. You can find that for many of the cases, the segmentation task is far from the ground truth. This is actually no surprise because SAM was trained on natural images, which has a large domain gap compared to medical images. But this motivated us to think about how can we adapt SAM to accurate medical image segmentation. This was our major motivation to develop MedSam. We first created a large scale and diverse data set, including 1.5 million image mask pairs covering various all the commonly used medical imaging modalities such as MR, CT, endoscopy, ultrasound, X-ray, and so on. The dataset also covers the common cancer types. We also design extensive internal and external validation with 86 and 60 tasks respectively to benchmark the model's performance. After having this dataset, how can we train the model? The original SAM model was trained with over 200 GPUs. However, for most academic groups, we cannot afford those kind of computing. Then we chose to use transfer learning, allowing us to use the pre-trained model with a natural image instead of training from scratch. Specifically, we use the SAM's network architecture, including an image encoder to project the high-resolution input image to the low-dimensional image embedding space. And we also have the prompt encoder to encode the prompt. Here we selected the bounding box as a prompt because it can accurately specify the segmentation targets without ambiguity. Finally, we pass the image embedding and the prompt embedding to mask decoder to generate the corresponding segmentation masks. We conducted comprehensive experimental results to validate the performance of MedSam and compare it to original SAM together with some specialist models such as widely used UNet models and deep lab models. So in this figure shows the final internal and external validation results. One point denotes one task, and here we saw in the bottom of its figure we saw the ranks of the four different methods. So as you can see, MedSam ranks first place on most of the tasks. We also investigated the effect of varying training data on MedSam's performance with two ablation studies. Specifically, we trained MedSam again on 10K and 100K images respectively, and compared their performance with the MedSam trained on the whole training set. It can be found that the performance followed the scanning law, increased the number of training images, significantly improved the performance in both internal and external validation sets. Here are some demos to show MedSam's use case, and in those two demos, we saw how we can use MedSam to segment the gland in pathology images and liver and tumor in CT scans. All those examples are conducted in zero-shot manner. Similarly, we can use the model to segment the abdominal organs in MR scans and lung and heart in X-ray images. Furthermore, we developed a lightweight version of MedSam, namely Light MedSam. The motivation is that MedSam has a very heavy image encoder with nearly 80 million parameters. This means that the model relies on GPU during inference. However, in many edge devices, there is no, such as laptops, that don't have GPUs. So can we make the model deployable without relying on GPUs? To achieve this goal, we introduced a tiny VIT model and distill it in a teacher-student framework. The original pre-trained VIT encoder in MedSam serves as the teacher, and the new tiny VITs serves as the student. And then we pass the same image to both of the encoders to get embedding. And we optimize the network with the MSE loss, aiming to constrain the tiny VIT to output the same embedding as the original heavy VIT. After the distillation, we replace the original image encoder in MedSam with this lightweight tiny image encoder and fine-tune the whole framework again. Here are the final results. We compare the inference speed of Light MedSam and MedSam on both CPU and GPU devices, and you can find that the Light MedSam is nearly 10 times faster compared on both CPU and GPU. We use this model as a baseline and organize the international competition in 3PR 2024, aiming to further promote the development of lightweight segmentation foundation models. We provide a large-scale dataset with over 1 million image mask pairs from over 100, and we also provide a comprehensive list of more than 100 worth public datasets. Here are the final results. So let's first look at the 2D segmentation tasks. The top team achieved a very high average DICE and NS score with over 80% and cost less than 1 second to get the segmentation results. However, on the 3D segmentation tasks, the highest score is only around 0.75, which has a large room to be further improved. The reason is that all the models are built with 2D image encoders, which cannot capture 3D context information. Recently, we extended MASM to MASM2 to enhance its capability for 3D and video image segmentation. Again, we create a large-scale and diverse dataset, including 378K 3D image mask pairs for CT and PET scans, and 77K MR image mask pairs, and additional we have 76K ultrasound and endoscopy video frames. Compared to the previous MASM1, the network architecture has 3 major modifications. First, the image encoder was changed from vision transformer to hierarchical vision transformer, allowing us to capture multi-scale information from the images. The second, the model introduced memory attention, allowing us to consider the previous image features and the prompts together with the predicted masks of existing frames when predicting the new segment and new images. Finally, the framework contains a memory encoder and bank to store the low-dimension representation of the past image features and segmentation masks. We evaluated the model across various segmentation targets and modalities, and we also compared the latest SEM 2.1 model and the previous mini model in the 3PR competition. We also saw that the MASM2 achieved better performance across all those different modalities and segmentation targets. We also found that in terms of the performance distribution, MASM2 usually have the more compact shape, indicating that the model is more robust compared to previous social models. We further conducted several user studies to validate how MASM2 can assist or accelerate the data annotation. So here, this is an example to show the human in the loop pipeline, annotation pipeline for 3D latent segmentation. We first generate the bounding box form on the middle slice, and then we pass the image, 2D image and the box to MASM2 to generate a 2D segmentation. And then we refine the mask to get the refined 2D mask. After that, we pass the refined 2D mask to MASM2 again and propagate in a bidirectional way to generate the 3D mask. So specifically, we propagate a mask from middle slice to top and from middle slice to bottom. Then we can have the complete 3D segmentation mask. Finally, we revise the segmentation mask to get the final ground truth. We applied this human in the loop pipeline to 3 different modalities and annotation tasks. First is latent CT latent segmentation. We annotated 5,000 CT scans. The second one is liver tumor segmentation. We annotated nearly 4,000 MR scans. And last one is cardiac ultrasound image segmentation. We segmented the various heart chambers from around 1,800 videos, including more than 250K frames. Results for each dataset, we applied the human in the loop pipeline for 3 times. We also saw that with this pipeline, with the help of MASM2, we can reduce the annotation cost by more than 85% across all those your studies. We also incorporated the MathSim tool into various computing platforms such as 3D Slicer, Terminal, Jupyter Notebook, Guido, and Colab. This allows users to apply MathSim tool on local desktop and remote workstations. We are excited to see that our MathSim has already gathered substantial recognition in the medical imaging community. For example, currently it has received over 2,000 citations according to Google Scholar, and we also make our complete code base, including training, inference, and model weights publicly available on GitHub. Now, the repository has received over 3,600 stars. In addition to serving as a general segmentation model, MathSim can be also used as a general imaging encoder. For example, in last year's Mikai Young Scientist Award paper, they used MathSim as a general encoder to extract the features from ultrasound images. We are excited to see that this independent study show that MathSim has superior performance compared to previous segmentation foundation models. This work was also selected as one of the top 50 papers in the field of AI and machine learning by Nature.com editors. And we are also excited that this work was also highlighted by Computer Vision News, which is one of the largest media in civic community. Next, I'd like to share our effort in building foundation models for cell segmentation in high-resolution microscopy images. Cell segmentation has attracted lots of attention since this is a fundamental task for various image-based biological study. However, most of the existing cell segmentation methods are tailored for specific cell types or microscopy modalities. With so many algorithms in the hand, it's a non-trivial task for biologists to select the suitable algorithms or select the proper hyperparameters. This motivates us to develop a universal segmentation model for microscopy images. However, this is also very challenging. First, there are several reasons. First, the images are very diverse. So you can find that those images, the microscopy images, have very heterogeneous appearance because of different cell types, different imaging protocols. Second challenge is the diverse morphology. Many of the cells have round shape, but some of them have irregular or elongated shape. And last but not least, it's very time-consuming and expensive to create large-scale annotations. So to build foundation models, the first step is still to create a large and diverse datasets. However, it's impractical for one lab to generate such diverse cell experiments from different microscopes. So what we did is we reached out to the various bio labs all over the world and invited us to contribute their microscopy images. And luckily, we finally got microscopy images from 50 different biological experiments covering different cell origins, different microscope modalities, different stain types, and different morphologies. Currently, this is still the most diverse dataset in the community. We used this dataset to organize an international competition aiming to attract talents all over the world to co-develop the generalist cell segmentation model. Here are the final results, and the first place achieved a media F1 score of 0.9 across a very diverse testing set, which is very impressive. This work was also highlighted by Nature, and we also write a commentary to discuss the potential of foundation models for biological image segmentation, which was the most viewed commentary in that issue. Okay, now we have introduced our efforts in building foundation models for medical and biological image segmentation. The key message is that currently we can have one universal model that can segment so many diverse image types and targets instead of building specialist models. Next, I'd like to introduce our recent two works about using multimodal generative models for perturbation prediction and report generation. We have witnessed the significant progress in multimodal generative models, such as ChatGPT and Cloud for text generation, DALL-E for image generation, and Will for video generation. Here is my personal example about how I improve my drawing skill with the generative model. The task is very straightforward. How to draw a horse. So first I draw 2 circles, and then I add the legs. After that, I draw the face. Next, I add the hair. And finally, after adding all the details, we have this cool figure. 3 years ago, this was a joke if I saw this example, but now it has been the reality. So, but how can we use this technology for healthcare? One promising direction is to build an AI water cell. What is water cell? This is a broad concept, but essentially, a water cell is still a deep learning model, but it can represent and simulate cell behavior at different scales and modalities. On our side, we mainly focus on the microscopic images. Specifically, we want to understand how cell morphology changes under different perturbations. We build this generative AI model that can simulate different cellular phenotype changes under various chemical and genetic perturbations. The framework contains 4 major modules. First is the encoder and the decoder. We project the high resolution image into the embedding space with the encoder, and then we can also reconstruct the high resolution image by passing the embedding to the decoder. Next module is the diffuse model in the latent space. So we have the forward diffusion process to convert the embedding to the a noise representation. In the reverse generative process, we can generate the meaningful embedding from the initial noise embedding. In this process, we also have an additional perturbation encoder to encode various chemical and genetic perturbations. And then we can use the perturbation embedding as a condition in the generative process. After obtaining the embedding in the latent space, we can pass it to decoder to generate the high-resolution microscopic images. To summarize, the main capability of this generative framework is that the model can generate high-resolution microscopic images based on various perturbations. We conducted extensive experiments to validate the utility of the model. First, we computed the features between generative images and real images. Here, the yellow points denote the features from our method. The blue points denote the features from real images. And we also have the green point denote the features from previous sorter methods. You can see that features from our generative images align with the features from real images very well. Here we also saw some examples of the generative images. You can be found that our images have high fidelity compared to the real images. Another application of multimodal generative model is for radiology report generation. Report generation is one of the most common tasks in clinical practice. After the patient completes their imaging examination, doctor need to write a report to describe the findings and impressions from the image. Those reports can be used for diagnosis and treatment. Those are also very important document for communication among different healthcare teams. Here is our vision language multimodal model for radiology report generation. We feed the image together with the mask to the image encoder to get embedding, and then we have the projector to project it to the large language model token space, and finally we fine-tune the whole pipeline for report generation. In this framework, there are lots of warrants for different modules. For example, we have different projectors, different large language models, as well as different fine-tuning protocols. We conducted a comprehensive study to analyze the effect of those different modules, and we applied the best protocol on this competition about abdominal CT image report generation, and we ranked second place in this competition last year. And here are some quantitative results. Compared to the 9-year baseline, our framework improves it by over 10%. But I want to highlight that radiology report generation is still in its infancy. But I strongly believe that the multimodal large language model has great potential to help radiologists to draft the initial reports and ultimately reduce the radiologist burden. Finally, I'd like to introduce our recent work about agentic system for X-ray image analysis. There are lots of, so what is an agent? There are lots of definitions. Essentially, agent is just a large language model using tools in a loop. Usually, an agentic system contains 4 modules. First is planning. It can separate the complex task or the queries from the users into several subtasks that can be solved by various tools. And second is the memory, which includes both long-term memory and short-term memory, allowing the agent system to remember the past operations that could be helpful to answer the latest questions. Next module is tool use. The agent can incorporate various tools to augment its original capability. And the last is action. The agent should correctly execute the tools by passing the proper arguments. Here we build a reactive framework for the X-ray to serve as the X-ray agent. In this framework, we incorporate various X-ray image analysis tools, including visual QA, report generation, segmentation, grounding, classification, and image generation. This is also the unique advantage of the agent system. We can incorporate all the state-of-the-art AI models under one framework, and the agent will use its brain, which is essentially a large language model, to incorporate those tools to address the user's questions. Here is the demo to show its interactive flow. And user can send a question, for example, ground main disease in this X-ray image, and then the agent will call various tools will first call diagnostic tools to analyze the image to find the most possible disease, and then you can also call grounding model to highlight the regions of the disease. And moreover, we can also further ask questions, for example, to ask the agent to segment the affected lung, and then the system will call the built-in segmentation tool to generate the lung mask. Here is a video to show its use case. Users can simply upload an X-ray image and then ask various questions. For example, diagnosis this chest X-ray image, and then the agent will call the classifier tool and the report generation tool to analyze all the possible disease. It can also ask the agent to generate a segmentation mask or use grounding to highlight the regions with disease. And so to summarize, today we introduced the foundation models for medical and biomedical image segmentation. The key message is that now we can build one universal model to segment so many diverse images and segmentation targets instead of training lots of specialist models. We also saw some examples about using multimodal generative models for the perturbation prediction and report generation. But I need to, it should be noted that those applications are still in its infancy. But I believe that with more and more powerful vision foundation models, large language models available in the community, those multimodal models have great potential to reduce experimental cost and also the radiologist's burden to write the reports. And finally, we saw our current prototype about building an agentic system for X-ray image analysis. We can unify all the state-of-the-art X-ray image analysis, X-ray image AI models under one framework, and provide great user-friendly to call those tools under one framework. Users just need to use text to describe their needs instead of without caring about the behind the environment. Looking ahead, we are working on creating an open platform to create community efforts to solve the challenges in medical image analysis together. For that challenges, what we have been doing for 5 years, its mission is to work with the global research community to come together, to think differently, and to solve the challenges in medical AI, ultimately transform outcome for people affected by cancer. We started this competition in 2021, and instead of only focusing on the accuracy, we also focus on the algorithms efficiency, such as the runtime, the GPU or CPU consumption, the generation ability across the external data sets. In 2021, we provided 511 CT scans and focusing on the 5-organ segmentation. And then we gradually expanded the dataset to 2,000 cases in 2022, and we also increased the segmentation targets to 13 common abdominal organs. In 2023, we further expanded it to joint abdominal organ and leg segmentation, and in 2024 we focused on the pancreas segmentation in CT scans by providing over 10,000 CT scans. And this year we introduced more interesting tasks such as the multimodal model and agentic system. So currently the registration is still open, so welcome to join us if you are interested in those tasks. Another ongoing work is to build a multi-agent system to serve as an automatic discovery engine in cancer research. Now we have so many unimodal foundation models for various tasks such as segmentation, classification, detection. We also have lots of multimodal foundation models such as report generation, vision, QA, image generation, and importantly, those models are becoming more and more powerful. Then, if we can incorporate those foundation models under one agentic system, those provides a huge opportunity for automatic discovery. If we can deploy those kind of agent on entire healthcare system scale data, we can use them it could enable automatic discovery of new cancer types and treatment strategies. Finally, I'd like to highlight 2 collaborative projects that we did at UHN. As I highlighted in the beginning, I hope this presentation can motivate more collaborations between AI Hub and other UHN department. So this was a joint project with Dr. Amin Madalin's lab. The task is to segment the go and no-go regions in endoscopy videos. We developed a deep learning-based model that can segment those 2 regions in video in real time. So compared to the previous algorithm, our segmentation results are much more stable. Another example is to develop an AI model for vessel segmentation in surgery planning. Previously, this task is conducted in a semi-automatic way, and which costs over around 25 minutes for just one case. But now with our fully automatic pipeline, and we can directly segment the 2 groups of vessels in around 1 minute. In addition to collaborations inside UHN, we are also very open to global collaborations. Here are 2 examples about building foundation models for about building biomedical image segmentation foundation models. And so again, the prerequisite to build a foundation model is to create a large-scale and diverse data set. But this is very challenging and almost impractical for one center or one lab to generate those kind of diverse images. So we said we during the past 3 years we have collaborated with diverse medical centers and universities all over the world to collect the diverse data set together, and also invite the researchers all over the world to co-develop generative AI models. Here are the available resources for what we developed at AI Hub, including various models and datasets. For the MSM series, we have open sourced the complete training and inference code, and as well as the model weights. We also released several datasets such as liver lesion segmentation MR data, deep lesion CT data, hard ultrasound video, and the recent Luna 25 lesion segmentation datasets. So we also have released the cell segmentation microscopy image dataset, which is currently it is still the most diverse dataset in the community. And we also released the pan-cancer CT segmentation dataset, including over 10K annotated CT lesions. Currently, this is the largest and the most diverse pan-cancer CT dataset in the community. And we also released the dataset to build the 3D biomedical image segmentation foundation model contains over 1 million image mask pairs. And the code of our multimodal models and the agentic system are also publicly available. So I also want to quickly highlight our recent workshop we organized last month about foundation models for medical reason. So this workshop was organized on CVPR, which is the largest conference in computer vision. So here are some quantitative numbers to show this conference. In terms of the H5 index, this conference ranked second place among all the publications. We are fortunate to have so many great speakers, and that they give lots of great insights about the foundation models in pathology, radiology, and agentic systems. We have made the video recording publicly available on our workshop website. So welcome to check it if you are interested in. And finally, I'd like to take this opportunity to thank the whole AI Hub research team led by Dr. Shaf Savji and Dr. Bo Wang, and I also highly appreciate the great support of all the amazing team members. Yeah, due to a time limitation, I didn't mention too much technical detail for those AI models, but all of them are publicly available and on GitHub. So welcome to check it. Yeah, finally, also hope you have learned how to draw a horse. And if you are wondering why I learned to draw a horse, this is because it is my last name. And that's it. I'm happy to take any questions.
That's great, Jun. Thanks for the great talk. I did not know that Ma means horse, so I learned something new. That was really great. If you have any questions, feel free to enter them in the chat or the Q&A. Individuals are muted right now, so if you want to come off mute, just raise your hand and happy to do that as well. So there was one thing that was mentioned in the chat. Jun, fantastic talk. Big fan of your works. We lead an AI lab for responsible autonomous systems in healthcare in India. Did not see many collabs from here. Happy to collaborate if interested. And the LinkedIn message is in the chat. Jun, if you want to take a look at that.
Okay, 1 second.
All right, we've got a question from Ali. I'm going to unmute you. Ali, go ahead.
So thank you so much, Jun, and I'm a big fan of your work. Thank you so much for doing LDUHN AI Hub for doing all of this. I just want to ask, like you showed that you deployed on a medical device. It was on premise. do you usually convert MedSum to ONNX and able to achieve that?
Currently, instead of do the format conversion, we mainly focus on develop a lightweight model. Since if a model itself is lightweight, we even don't need to convert it to like some format like ONX. Currently, for the 2D image segmentation model, I think the efficiency should be good enough. For example, for the light MSM or the efficient MSM model we released last year, it can even on the laptop the inference latency is less than 1 second.
What I meant, so you use like toolset or to put it on premise on a medical device in case you want to deploy it, or do you convert the model in case you want to deploy it, or you keep it like in .pt form?
No, we didn't convert it to ONX. We just keep the original PyTorch format to maintain the flexibility. But we mainly focus on to make the model itself really lightweight.
Okay, thank you, John.
Yeah, thanks for your question.
Great. Any other questions from the group? I have one while individuals are thinking. Jun, how do you think all these foundational models are going to change how we do basic science and how we generate hypotheses? We've got a lot of researchers on the call. Maybe you can speak about where researchers should think about incorporating large language models in kind of their day-to-day. And I know research has adopted quite a lot of AI, but if you can maybe comment on that.
Yeah, this is a great question. I think with currently we have more and more foundation models for various tasks in the community, and next I think the next key direction is how we can incorporate those foundation models in one system to enable the end-to-end workflow for the to generate hypotheses and validate the results. So in my view, agentic systems provide a unique opportunity for those kind of tasks. Instead of build the traditional rule-based system, agentic system can use the capability of large language models to encapsulate all the tools and analyze to intelligently analyze the user's queries and select corresponding tools to solve for both hypothesis generation and validation. I think I strongly believe that agentic system provide a huge opportunity to serve as an AI scientist.
Agents are the buzz right now. Everybody's exploring how we can move forward with agents. We have one more question in the chat from Zina. Thank you for your great talk, Jun. My question is, how does MedRax handle uncertainty and ambiguous images? Does it defer to clinician input or use ensemble reasoning strategies across models?
Oh, this is a great question. So currently in the we address the uncertainty and hallucination based on 2 points. So first we incorporate all the state of the art models in the MedRax framework, which means that for each individual foundation model or X-ray image analysis tool, it is already the state of the art model, which has a relatively higher accuracy in terms of the disease diagnosis. And secondly, we also the agent is a human. It can incorporate the human feedback instead of directly only relying on the output from various AI models. So a human or medical experts can play a key role in this pipeline. And the final, so essentially, MedRax is an assistant. It's a copilot. We will build it to serve as a copilot instead of replace the radiologist. The final decision will still be verified by clinicians.
All right, hopefully that made sense because that was way over my head that way. Are there any other questions from the team? Thoughts? Ali, you can go ahead again.
Yeah, so I just want to ask, in video tracking, like when you put sequences, like I know when they went from SAM to SAM2, they added this memory encoder and it propagation. Do you really think there's similar model that uses this attention and this propagation for object detection? Or do you think that SAM 2.1 and 2 are like the state of the art for tracking in videos for medical images, like MedSAM 2 and MedSAM 2.1?
So your question. So let me first clarify your question. Your question is about the object. So for video segmentation, your question is about the comparison between the detection-based method and the tracking-based method. Is this your question?
Yeah, because it has some memory. So do you think like this MedSAM 2.1 is like state of the art tracking for tracking in a sequence of? Yeah.
I see. I got your question. Yeah. So currently in either SAM2 or MedSAM2, the memory bank only contains 8 frames. So for it works well for the for general for common short videos, if we only have 100 or 200 slices or frames, it works well. But for very long videos, even for some videos, the object shape or object could appear and disappear. For those kind of applications, we may need to improve the memory. The default 8 frame or 8 slice memory may not be enough.
So you can actually make it longer, like 12 or 20, but you would need more GPUs, most probably. Yeah.
Correct.
Okay. Thank you. Thank you. It's cool. Thanks.
Thank you.
All right. I don't see any other questions. So with that, I want to thank Jun so much for sharing all the incredible work that you've done over the last few years. It's really impressive how far you've come along and how quickly the work's been done. And want to thank Agatha for helping us coordinate this event and everybody for attending. If you have any questions, feel free to reach out to the AI Hub. But with that, we'll wrap things up. We're going to take a break for August, but we have some exciting rounds coming up that we're scheduling for September and into the fall. So stay tuned for those. Thanks, everyone. Have a great evening.
Okay.
Thanks,
Thank you so
Jen.
much.
Yeah,
Thank you.
Bye.
Bye.